Right, let's talk about the potential energy of the ocean, or basically the tidal power. So the surface of the ocean will go up and down, and the difference between two highs or two lows is 12 hours 25 minutes. And this place can be really very high. Okay, and so to reduce this potential energy, you need it to be 5 meter or higher. That's what they say over here. And there are like 40 places in the world where 40 sites in the world where this is actually very useful, and you can actually practically use it. So why this is happening? It's happening because the position of the sun and the earth and the water in the on the earth. So we are looking down to the earth. The north pole would be here, and the earth would be rotating around itself like this. So those people over here are having their noon, those people are having their midnight away from the sun. Those are sitting at 6 p.m. and those are at 6 a.m. And so because of the position of the sun, it will pull on the water of the ocean. And so here you'll have the high tide, and here you'll have the low tide. Low tide also over here, and this is high tide. So you have two highs and two lows during this cycle. And now if you add the moon as well, and the moon is rotating around the earth, so here when there is new moon, so you will not be able to see it, and here when it's full moon, so that's the big circle, you know, we will see it, and the first quarter and third quarter. So when the whether the moon is in full moon, new moon, or full moon, he is at the same, he will act together with the sun, and you get a boost to the high tide. And when he's in the first quarter or third quarter, he will counter act the sun, and you get a little bit weaker tide, and that's why. So you get boost from the moon in new moon or full moon, and you get lower tide when you are first quarter or third quarter. At the end, the ocean basically we surface will rise up and down, and we have, he suggests there are three ways to actually harvest that energy, right? So the first is just building a dam and accumulate the water behind that dam, and then it just become a hydraulic turbine project, you know, where you have high water, and you are basically wanna send it through a turbine. So here is high water, and the difference between the high level and the low level is, let's call it R, that's the tidal range. And so you fill this tank when, or this big actually basin, you fill it when you are in high tide, and you wait until the water on the other side go to the low tide, and now you have R. That is the potential energy that you can use through this hydraulic turbine. So how much exactly, how many joule do we got over here? Well, the potential energy is mgz, mgz, right? And so because it's different height, he will basically just take a small element at dh, and he will calculate the mass in that place, so that the dm is rho a dh, where the area is this big basin area, you know, the big area behind the dam that you are accumulating the water in, and the h is the height of that element, and then he will add all of them from 0 to r, or basically integrate from 0 to r of this, and so it comes to g rho a h dh. And so basically you're integrating h dh. What's the integration of h dh? H square over 2, right? And so since you are doing from 0 to r, become r square over 2. So at the end of the day, how much energy we storing over here? It's the mass rho a r times g time r over 2, r over 2. Why over 2? Because that is the center of mass of the water, right? It makes sense. So this is how many joules we got, the center of mass times the mass of the water in that place. So those joules, you wanna send them in very quickly. Why very quickly? Because if you wait, that low tide will start rising, and you're not gonna have R anymore, right? So that time span that you're gonna expend all those joules or harvest those joules through the turbine will determine the power. So if you make them very short to harvest all the R, that will result in big power, which mean big turbine, which mean higher initial cost. And also the bad news, if you make this delta T shorter so that you can harvest all the R, is that you will spike the power, and then for a little bit longer time you are not going to have anything, right? So which mean you need energy storage to help you when there is no power generated. And as we learned in solar energy, batteries are expensive. We wish we would soften this area a little bit, right? We wanna reduce the peak over here so that the term is not expensive, and we wanna get a little bit more energy over here. So how do we do this? So people could actually say, well, let's actually just let the flow rate go slower so that you can take a little bit fill this gap, huh? But if you wait really long enough, then the high tide will start rising, and you are basically losing your potential energy. So a better idea is that big lake or big reservoir that you build behind the dam that's connecting you to the ocean. The ocean is over here, huh? So that big area you you divide into two, and that is the high pool and the low pool. And so the high pool is always getting water, not always, he's getting water in the high tide, and the low pool will take water off basically, or reject water during the low tide. But as a result, you always have high pool and low pool. I mean, difference will vary a little bit, but you have continuous generation of hydraulic energy, right, between those two guys. So now the problem with all tidal power is the initial cost, of course, because we said the fuel is for free. The ocean will always have the tide. So the problem is the initial cost, and so people can make this a little bit cheaper if they already have a big gulf or a big place where all you need is a small dam to build, rather than let's go and just build our own reservoir in the middle of the ocean, right, or like near the shore. So the people who are lucky to have this and build those facilities, you can see them over here, and those sites can generate up to say 240 megawatt, like in France, for example, right? And so here is the range of the tides in those sites. And here is a picture of one of those hydraulic dam that they build with a hydraulic turbine over here. And so sometimes you get lucky because you have all that area already, and all you just need to do is just building a very tiny wall, right? And you can see this is where the ships will cross, or the boat will cross from the ocean into the bay. And so when you are lucky and you have the area like this, you can expect the energy cost to be really expensive. Where is the cost coming from? The initial cost, the operating cost, and the maintenance cost of the turbine. So 1.4 cent per kilowatt hour. So that's pretty neat, right? So the second way to harvest that energy, the tidal wave, water is up and down, going up and down, up and down, without building an actual dam, because that would be really expensive, is to do a tidal fence. So notice that there is no big reservoir that we are building behind, but it's just that we are harvesting the motion of the water up and down, up and down. So what is that hydraulic fence? Well, that hydraulic fence could be filled with basically a bunch of turbines. And whether the water is going this way or that way, those turbines are designed to rotate in the same direction and generate electric power from them. And that's not science fiction. There's actually a patent for those hydraulic turbines. Alright, those are similar to the helical vertical axis wind turbine that we saw, right? Remember the one that was rotating like this? And those will rotate always in the same direction, whether the wind was going this way or that way, with the same thing for the hydraulic turbine as well. Okay, so then what's the problem with this? Again, the initial cost, and whether you'll be able to at the end of the project break even and save money, right? What is the initial cost of this? How long it will survive in the corrosive water of the ocean, and how many kilowatt hour will you produce at the end of the lifetime of the project. And you divide the total cost over the kilowatt hour, and you figure out how much did you spend on each kilowatt hour, right? The third way he was talking about over here. So we talked about the dam, talked about the tidal fence, and then there is a tidal turbine. So if you think, and you are right, that tidal fence will also be expensive, so similar to this, well, we, in order to harvest wind energy, we don't build a wall filled with wind turbine. We just put one wind turbine and we get energy out of it. So what is the problem with just putting one hydraulic turbine and harvest the current, the water current, since the water is going this way, that way, this way, that way? And that is exactly what this thing is, tidal turbine. So those will be something like this, and when the water come, this guy will be facing this way and he will generate energy, and when the water come from the other direction, this guy will rotate and harvest energy from the other direction. So exactly like a wind turbine, except that this guy is even better. Why? Because remember, the input power to a wind turbine was, if I have a wind turbine with a radius, with a cross section area A, what is the available input power to it? Half rho A V cube, right? Half rho A V cube. Well, that rho in case of water is not 1.2 anymore. It's even not 997 anymore. It's bigger because it's ocean water, salty water, which is even more heavier. So that basically means that this guy is saying that with 15-meter water turbine, you will expect the same power you get from 60-meter wind turbine, right? So there is kinetic energy, and we can harvest it. Only challenge is, are your design gonna survive long enough so that at the end of the lifetime of the project, the kilowatt hour cost is as competitive with other energy source? And again, for some communities where they don't get their energy cheaply, those technology could actually break even with them. It could really make economical sense to them, right?